Hey guys, this is Tyagi and welcome to our new YouTube channel, Learn Comparative Programming with CodeChef. If you're into data structures and algorithm, then this is one-stop destination for you. Every week we're gonna post new videos on problems and their solutions, problem-solving paradigms, live problem-solving sessions, and much more. So if you're interested, just hit that subscribe button and that bell button. So without further ado, let's start. The problem that we're going to do today is Robot Detector, UKROBOT, and the difficulty rating that I have assigned this is 1500, so it's easy. And the prerequisites are none. There are no prerequisites to solve this question. So let's try to look at the workflow of how things are going to go while solving this question. So firstly, we're going to understand and read the problem statement. Secondly, we're going to build some intuition on how to solve a particular subproblem, and then we're going to expand our solution for the whole problem. Then we're going to look at the pseudocode and the implementation details as well. So let's start. So this is the problem statement. So if you haven't already read the problem, I suggest you to read the problem once and then come back to this video. So let's get started. I'll just explain the problem once. So we're given a robot which is in cell 0, 0 of an infinite grid. So it can go anywhere on that infinite grid. It is currently at 0, 0 when it starts. And one cell x, y contains an obstacle and all other cells are free. So there's only one obstacle out of that infinite grid, and that it belongs from, like, the x coordinate belongs from 1, c, and the y coordinate belongs from 1, r, and these c and r will be given to us. So this is the only thing that we're going to be given in the question in each test case. So and that is the like the boundaries on where this blocked cell might lie. So it's so that x will belong from 1 to c, and that y coordinate of that blocked cell will belong from 1 to r. Now we have to give some sequence of instructions to that robot, and those sequence of instructions will involve 4 letters, L or left. That means that you move one cell to the left, and that is you decrease the x coordinate by 1. Secondly, you move right or R. So similarly, you move, like, increase the x coordinate by 1, move to the right. Thirdly, it's down or D. And in this sense, the y coordinate decreases by 1 and you move one cell down. And U or up, you move one cell up and you increase the y coordinate by 1. So the robot attempts to perform these instructions one by one. So what happens if it's trying to go into a block cell? Then what happens? So if the cell it needs to move is free, then it will move on to that free cell. But if you're trying to move that cell up onto a cell which is actually blocked, then that cell, that robot will stay in that current cell. So it won't move towards that blocked cell if we're wanting it to move towards a blocked cell. I'll explain what this means in shortly. Let's just complete finishing reading the state problem statement. So consider the following process. You choose a fixed sequence of integers for the robot. So we give the string s, which consists of only these 4 letters, L, R, D, U, and this is actually an instruction for the robot to follow in that particular order in which we give it. So which performs these instructions, then you're given the final cell of the robot. So after performing these instructions, we will be given, like, we won't be given, but if you're given the final cell of the robot, and based on only that information, we need to determine the position of the obstacle. So our problem is basically we have to give a sufficiently short sequence of instructions, which is shorter than 10 to the power of 4, and the limits for R and C are from 1 to 20. So it's not going to be more than 20 R and C. So we need to find a sufficiently short sequence of instructions such that if the robot follows those instructions and tells us where it finally ended up, we will be able to distinguish where that blocked cell's position is in that grid. So that is it. So we won't be given the final position of the robot. So, but the question is, if we're given the final position of the robot, then will we be able to distinguish where or pinpoint exactly where the position of the blocked cell is in that infinite grid? So that is the problem statement, and we have to craft that string, that series of instructions in such a way such that we will be able to do that. Okay, so let's move on to that question. Okay, so let's talk about what it means if I want to send a cell towards a point where it's actually trying to go. So let's suppose it's here, and we have a blocked cell, and we're currently over here, and the next instruction that is to be processed is U. So we're trying to go basically one cell up, but we can't because this cell is blocked. So what will happen right now is it will stay in this cell. If the next instruction to be followed is up, it will again try to go up, but it won't be able to go up, so it will stay in that same cell. So this cell is directly below this cell, so it will stay in the same cell. But if the next is right, then it will be able to go towards the right cell, and the robot will come over here. And because this cell is free, and actually it can move towards this cell. The only reason it couldn't move was because this is the blocked cell and it can't move towards that spot. So this is what it means when they say that if you try to move the robot into a cell that is blocked, it will stay in its current position and it will not move. Okay, so let's begin. Suppose, let's for the sake of this example, let's suppose that the position for, so this is a 4 cross 5 grid, so there are 4 rows and 5 columns, and this is an example test case. So this is our starting point, the starting initial position of the robot. So each cell denotes a coordinate, and this starting cell denotes the initial coordinate, that is 0 comma 0, and this cell is 1 comma 1. And our so this is an infinite grid, so all of this is an infinite grid, so it extends towards the right, up, left as well, but I've drawn only these cells. So, and this, if you see this red label, red marker, red boundary, this is the position of where the robot might lie in. So out of these 20 cells, the blocked position will be one of these cells. So one of these cells will be blocked, and we have to find out this information based on the sequence that we given. So we have to give the sequence in such a way such that if the final positions of the robot are given to us after performing those moves, then we'll be able to distinguishly figure out where the cell was. So basically how we do that is, so if for a sequence of S that we give to the compiler, and we have like two options. Suppose the first one is here, so if the current cell block was here, then the final position will be x1 comma y1 of the robot, and if it's over here, it will be x2 comma y2. Now the reason of how we're going to solve this problem is that we have to make sure that for every possible blocked cell, the value that they end up in has to be different. So for any two cases, these two can't be equal. If these two are equal, then basically this information, if this is given to me x1 comma y1, and if the block cell is here or here, both of them end up in having the same final position, then I won't be able to distinguish whether the block cell is here or here. So that's what we have to do. We have to find out and figure out a way for us to say for sure that where the block cell is, and that is our agenda. So let's move on. So let's try some intuition. Okay, so let's fix a point of where block cell is. Suppose the block cell is let's say here. This is the block cell that we're talking about. Okay, so this is the starting point. So we have to, let's try to break it into a sub problem of, can we figure out which row it lies in. So this is row 1, this is row 2, this is row 3, this is row 4. Okay, this is column 1, this is column 2, this is column 3, this is column 4, and this is column 5. Okay, so 5 columns and 4 rows. So can we figure out the row, in which row this block cell lies in, and how will we do that? Okay, so what happens if we perform symmetric moves? Now what do I mean by symmetric moves? Suppose my starting block is here, and I execute a move of like row amounts of ups, that is 4 in this case. So 4 ups and 4 downs. What happens in this case? So what happens in this case is, let's try to perform these activities. So it goes up 1 by 1, it moves here. So 1 up, 2 up, 3 up, and 4 up, and it will reach here. Okay, so after these 4 ups, let's perform these 4 downs and try to sweep this entire column at once. Okay, so it'll perform 4 downs and it will come down 1, 2, 3, and 4, and it will come back here to this position. So back where we started from, we end up here by using these symmetrical moves, 4 ups and 4 downs. But this is only the case when there is no blocked cell. So because there is no blocked cell, none of these moves got blocked, none of these moves were not be able to perform. So all of these moves were able to be performed, and because of that, and because of them being symmetric, so the y coordinate increases by 4 and then decreases by 4, we always end up in the same place. Now let's figure out what will happen if we encounter a block position while performing the symmetric move, and let's do that with the example of here. So for here, let's start again and perform these 4 ups. So we'll perform first up, it will come here. Now when we perform the second up, we won't be able to perform the second up, it will stay here, because the rest 3 ups we won't be able to perform. Why? because the next up is up, and we won't be able to. Let's write this down: up, 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 down, 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 down. So this is our first up. So we performed this. This is our second up, but we won't be able to perform this up because currently we're in this cell, and by doing an up, we're trying to go into a block cell, and which is not allowed. So it will actually stay here. So this up will never get executed. Similarly, this up will never get executed, and this up will also never not get executed. These three ups did not get executed. Now what happens is we execute four downs. So we do first down, second down, third down, and fourth down, and we end up here. Okay. So as you can see, after I performed this, after I performed a symmetrical move, there were certain number of ups which were not able to be performed because the block cell was that down, because the block cell was at that position in the cell where I was trying to go to. And in that sense, we always see that this difference, if it started from 0 comma 0, it is at -3. So the x coordinate, by studying the x coordinate, we can tell where the row is, right? So if we know that it lies in this column, if the block cell is in this column, and if we try to perform several moves, by realizing how many number of moves were blocked, so because it is -3, three ups were missing, and because we know that three ups were missing, that means it had to be three down. So it had to be, so it, if there was no block cell here, it should have been here, but it didn't go here. So one up was blocked, second up was blocked, and third up was blocked, and that means that all of these three cells went unvisited because this cell was a block cell. And henceforth, by studying the x coordinate of where it ended up, when I know the which column the block cell exists in, this difference is basically 3, and which is the row number. Let's denote the block cell by r dash. So this is the r dash value. So if we know which column it lies in, we are able to assume, we are able to figure out which row it lies in, right? And that is the difference between the x coordinates of the starting position, which is 0 comma 0, and the ending position, which is 3. So let's do this. So what we're trying to do is we're trying to basically sweep, we're trying to come across and perform on one column such that we have a block cell in it. So we want to sweep the entire grid, this entire red thing that we have over here. So we want to like sweep by across this entire red grid to make sure that we encounter this block cell, because it's only when we encounter this block cell that some of the up moves will not be able to, manifest, will not be able to perform. So, and that's how we know where the ending position is. So we want to encounter this block cell at least once. So how can we do that is, so we start from here, we start from this position, and what we can do is we can perform this four ups and four downs, and then, so this is a pseudocode. So for I in 5, for I in 5, that means 5 times. We run this loop 5 times because there are 5 columns, and in each move, what we do is we do 4 ups, 4 downs, and 1 right. So what we're doing is basically, if we're here, we go up 4 ups, 4 downs, and then 1 right. So we do this once, then we do this again twice, thrice, 4 and 5 times. We do this 5 times because the block cell can be here as well, and we want to visit this column as well. So we have to do it the number of columns wise. If we start here, remember this starting position is at 0 comma 0, but if we do it at 1 comma 0, then we have to do it 5 times. So we can just move this 1 right by adding 1 right initially in our argument. Okay, so what happens then? So let's complete this algorithm. So it ended up right here. So let's see what happens then. So it does 4 ups, 4 downs. It came here, and 1 right. It ended up here. So 4 ups again, but it couldn't perform those 3 ups, and then it performed 4 ups, like 4 downs, and then it came here, and then 1 right. Then it came here, and now again it will perform 4 ups. 1, 2, 3, 4, 4 ups. It came here, and now it will form 4 downs. 1, 2, 3, 4, 5. So this is 4 downs, so it will come here, and 1 right, so it will come here, and it will again perform 4 ups, end up here, perform 4 downs, end up here, and again do this 4 ups, end up here, 4 downs, ends up here. So as you can see, we missed, so one second, as you can see that we clearly missed like these blocks. And the reason for missing these blocks was we already encountered one a blocked cell, and because there is only one blocked cell in this infinite grid, I don't actually care about these missed pieces, because I'm pretty sure that there is no blocked cell over here, because the blocked cell is already encountered. We already encountered the blocked cell before, and because we encountered the blocked cell, that is the entire reason of why this got, like, this part never got addressed. The robot never came into these grids, these cells, and I don't care for it because I've already encountered this. Okay, so after I do this loop five times, what happens then? So I'm going to end up at this position, and it's going to go one right as well, so it'll go here. So after I do this, after I come here, by studying the location, so I know that the y coordinate will always be, since I know the number of writes that I'm executing is 5, I'll always know that the coordinate so my starting coordinate was 1 comma 0. So 1 comma 0, and it went 5 writes, so that means it went to the x coordinate, to the x coordinate of 1 plus 5 6, and the y coordinate will actually depend upon where the block cell is. In this case it's minus 3, so this point right here is 6 comma minus 3. And studying the y coordinate in this case, we can tell, because the initial y coordinate was 0 and the final y coordinate is minus 3, that means there were 3 ups that could not be performed. That means the row number of our block cell is 3. That is how we know, because there were 3 ups that could not be executed. So now what? So now we are in a position that we have solved for this subproblem. So what we mean is, if the question to us given was that it only figure out which row it belongs in, the robot, then we'd surely be able to tell which row. We'll follow this algorithm 5 times, we'll follow this loop 5 times, and if we give this string, then depending upon the where the initial robot was, it will end up here. If it was in this row, this point, this row, this row, this row, this row, or this I mean this entire row, out of all of these cells, if it was in any one of these cells, the ending position will be 6 comma minus 3 for each and every one of those cells. But if it was this cells, then only 2 ups could not have been performed, then the final position would have been 6 comma minus 2. So the final position can be anything. So the final position, depending upon which row it ended up in, is in the 6 coordinate, x coordinate, but which the y dimension, y coordinate of this final cell will depend upon which row it started in, which row the block cell was. And so we have figured out a way for us to calculate which row it exists in. Now let's try to calculate. So this is the block cell. So let's try to find out the column as well. Okay, and how will you do that? So if you can just invert, if suppose we started over here, and if we just inverted this entire thing by 90 degrees, it is the exact same algorithm that we just did right now. But the only difference will be that the rows will be converted into columns and the columns will be converted into rows. So then if we do it again, so this is only in condition to if we know where we are, if we know that where the S is, right? So if we know where it ended up, right? So suppose we know that the after performing this step and after knowing which row it belongs in, if we know for sure that this is the if we somehow were able to navigate this robot into coming over here, then we can perform the exact same thing as it was over here. So it's just like we're viewing this from like this angle. So if you just rotate your screen, you can see that this starting position, this position corresponds to this position, and this entire block is actually rotated and inverted by 90 degrees. And if we do the exact same thing, it's just with minimal differences. So what we'll do right now is, suppose suppose we're here. So now what we'll do is, if we follow this algorithm for I in 4, we do 5 lefts, 5 rights, and 1 ups. If we do this 4 times, why 4 times? Because now there are only 4 rows: first row, second row, third row, fourth row. So I only have to do 4 ups, right? So if I came over to this point, I'll do 5 lefts, 5 lefts, it'll go 5 lefts. So one second, let me draw this out. So if it goes 5 left, so it will go first left, second, third, fourth, fifth, it ended up here. 5 rights, first, second, third, fourth, fifth, it ended up here, and 1 up, it ended up here. Okay, so this is one loop. Now let's again do this one loop, and this loop had it ended where it started. The 5 lefts and 5 rights cancelled each other out because there was no obstacle in the path. Now let's see what happens when there is an obstacle in this case, and we want this obstacle to be this case because that is the only information that we're going to get of an obstacle coming into our path. So we want to make sure that an obstacle is in the sequences, so the obstacle is encountered in the sequence that we give. We have to make sure of this fact. So let's do 5 left and 5 right again. So we do first, second, third, and we couldn't perform the fourth. And the reason that we couldn't perform the fourth was because in the fifth cell there was a blocked cell. So it remained here. So let me write this down. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and 1 up. So it did first, second, third left. It did that, these 3 lefts, but then it wasn't able to do 2 lefts. So it left these 2, and then after coming to this point, it performed 5 rights. So it came first, second, third, fourth, and fifth, and it came here. So if there was a block here and a block here, so it ended up here. Okay, and we know that the reason of why the difference from the starting points, the x coordinate of this point and this point, the delta x coordinate. So in this case, this 3 was delta y coordinate. In this case, delta x coordinate will give us the c dash value of where it started. So this is delta x is not with respect to 0 comma 0, it is with respect to where we started, and that is that c plus 1th column. So we started the so the x coordinate of the initial starting point of this term of the algorithm of the second loop was from x equal to c plus 1. So because we started from here, because we ended up over here, so we start from here, and then because of which we do this thing, do this thing, come back, and then we know that the reason of this delta x change is because 2 lefts, as you can see, were not be able to be implemented because there came so this cell was not unvisited, this cell remained unvisited, and the reason why these 2 cells remain unvisited was because this value of c dash was actually equal to delta x, and because it was not able to come at this point, and that's why we can say that the c dash value is 2. And in this form we have completely reduced that r dash is equal to 3 and c dash is equal to 2, which is in fact the row number and the column number of this block cell. So this is what we were able to do. So one loop, the one thing that we missed right now. So the important thing is that we perform these symmetric algorithms, both of these symmetric algorithms, and we have to make sure that we encounter this thing once, right? So in this case, we did this loop 4 times because we were starting at this point, right? So we knew that we'd be able to sweep the entire of this entire grid, if we did this 4 times, because we knew first row, second row, third row, and fourth row. There are only 4 rows, and we're starting from the first row, right? But now after the first algorithm was implemented, we ended up, if you remember where we ended up over here, we can end up over here, we can end up over here, we can end up over here, and we can end up over here. So we can end up anywhere, right? We can end up at any of these points. So what we have to do is that, so if you remember the previous algorithm, it had like 4 downs, right? So we know that after 4 plus 1 downs, so because these 4 downs were implemented, so wherever it was, if I do this 4 up, I'll be able to encounter a cell, right? I'd be able to know if 4 plus 1 cell, if I go up by 4 plus 1, because suppose I encountered, let's say I encountered 1 second. Okay, so suppose we encountered a cell over here which is blocked, and then we try to move some up. So we're only talking about the first iteration of that algorithm. Okay, so if I, so which was 4 down, if I remember correctly, it was 4 up, 4 down, 1 right, right? So we did this 5 times because we were starting over here at this point and we know that there were 5 columns, so we did this 5 times, right? So what we're trying to figure out is how many times do I need to do the second one, right? So can I draw some correlations? So second loop, how many times do I need to run that loop so that I can be completely sure that this blocked cell came into my path. Okay, so in order to reduce that, let's see where it ended up, right? So when we talked about the y coordinate, we knew that the difference between the initial and the final y coordinate will give us the row value of where this block cell is. That much we have already figured out. But after we perform this 4 ups and 4 downs, after we perform some 4 ups might get eaten up, some ups might get eaten up because they won't be able to move. But when I'm in this point and because I'm blocked, so when I'm performing 4 downs, I'll be exactly 4 downs below. So basically it's 4 plus 1. So exactly my 4 plus 1 increase y plus 4 plus 1 will be the y coordinate of my blocked cell. Y coordinate of blocked cell. So this I know. So and this will, and I, since I can only encounter a blocked cell once, so when it moves towards the right and it performs symmetric moves, it always ends up with the same y coordinate. So it is symmetric in y coordinate. So this y plus 4 plus 1 is equal to yb will never change. So what I need to do is I need to, so let's see where it ended up. So we ended up over here in our example. So this is our endpoint after a first iteration of algorithm E1. So I know that exactly 4 plus 1. So first, second, third, fourth, and fifth. 4 plus 1, fifth cell. This is the row where the blocked cell is. Because after I encountered this blocked cell, I did 4 downs. First down, second down, third down, fourth down, and fifth down, and I reached here. And I know that 4 plus 1 above that will always be the blocked cell. And because it is all after this iteration, there will be no blocked cell which will come in my way. So it will always, and because it is symmetric, because 4 ups like uh, e destroy 4 downs equally, so it will always end up in the same y. And exactly 4 plus 1 y is up will give us the row coordinate of where this cell is, block cell is. So I only need to run this algorithm 4 plus 1 times. If I'm starting from this point, I don't need to change my point. I just start wherever I ended up. I just start from this point and I go and I perform this algorithm, this 5 lefts, 5 rights, and 1 up algorithm 5 times. And where did this 5 come? And when I do this 5 times, I'll be pretty sure that I encountered this blocked in my path, and this will be encountered in the last cell when it comes to this point. So it will go up, and so in a similar manner it will go up. So we did, from when we started from here, we did it for 4 times because we knew that if the block cell could be here, the block cell could be here, the block cell could be here. But when I've already performed the first iteration of the algorithm, I know exactly which row the cell is. So I don't need to perform and go and traverse this entire area as well, these entire grids as well. I just need to iterate this grid up until this grid because I want some of the left moves to get nullified and not be performed so that I can figure out the x coordinate of this block cell. And this is the algorithm. So let's walk over to the pseudocode. So the pseudocode is pretty simple. So our S is the string which we will output. So for I and C, so C columns first to start here. For I and C, we do for J and R we do up, down, J ups, like R ups, R downs, and then one right. Similarly, R ups, R downs, one right, R ups, R downs, one right, R ups, R down, one right. This part of the algorithm we perform, and afterwards we do an r plus 1 times because we know that the r plus 1 exactly, if we move r plus 1 ups, then we'll be in the same row of where we encountered our block cell when we ended up from this part of the algorithm. And then we'll do this move for j and c times. So this was c columns, 5 columns, so that's why we were performing 5 lefts and 5 rights. So c columns. So for J and C, S plus equal to L. For J and C, S plus equal to R. So 5 L's, 5 R's, and then 1 R's. And we perform this and we'll get our answer. So let's look at the let's look at the actual implementation. So this is an AC code that we've got, and it's a pretty small code. So it's nothing but the exact same things. So we take R and C, we input RNC, we take a starting like zero string. So this is an empty string, and then for the number of columns, we iterate over the first part of the algorithm, which is to figure out the row number of the algorithm of the block cell. So we do this R times, we do R ups, R downs, and one write, R ups, R downs, and one write, and then we end up C writes, and then after we've reached to the point over here, like we can reach at any point, we can come here, we can come here, we can come here and come here, depending upon which row it is. But it doesn't matter where we end up. We are pretty sure that exactly r plus 1 rows above us we'll be able to encounter the row in which the block cell is, and this is the last row that we have to traverse in so that we encounter the block cell. And because when we encounter the block cell, we'll be able to rectify some of the left moves that will be held when when it tries to move into a cell which is blocked. And by seeing how many moves are blocked towards the left, I'll be able to figure out which column it ended up in. And I'm doing the similar way. So this time the loop is not up until r, it's r plus 1. So after I do this loop for r plus 1, for c lefts, I do c lefts, I do c rights, and then I do 1 up, and then I simply output the string. And that is how we'll be able to figure out where if the ending position is given to us, we can figure out where the initial block cell was. And that is it for the video.